Right, we're off. So this is going to be part 2 of the simulation lecture. We'll finish that off today. I just did the head count. I think I said, was it 15 I decided? Yeah, 15. Okay. I just want to keep track. Right, so on Monday, part of what I was talking about was just trying to get you ready for actually making real simulation logic. And I started by just describing, well, this whole idea that games are a type of simulation, that simulations historically have often been one of the main cases for object orientation. In fact, object orientation was invented to help make writing simulations easier. The language Simula67 had some of the very earliest ideas that Smalltalk then developed into what we would think of now as object orientation. So that led to a bit of a philosophical digression on what objects even are. My main point there being that there isn't a hard and fast rule that tells you what your objects ought to be. You know, part of it is you kind of decide how you want to carve the problem up sometimes by matters of convenience, or maybe, you know, when you're doing like things like class hierarchies, you get some sense of relations between different types of things. And you try and map it all out, and then you create a world of objects in the hope that those objects can then kind of go about their business and interact with each other in interesting ways. That's what makes a simulation an interesting thing. We also at the end took a little bit of a return to this issue of, you know, making animations and so on, and this bit where if you're updating the state of your grommet entity from one frame to the next, you actually have to go and move all the tiny little parts, just a tiny amount. And that's really sort of true. Like if in a game, if you've got a character with an animated body, there is in fact a virtual skeleton inside there. And it turns out the way it's all done is it's all done with matrices. That every joint in the model has got a matrix associated with it. And what happens is when you're wiggling your little finger or something, there's a matrix. First of all, there's one big matrix that tells you where your body's positioned. There's another matrix that's positioning this arm. And then there's one in here, and there's one in here all the way down. So it's a tree structure. It's a tree of matrices. And as you work down it, each matrix gets multiplied by the next one in the chain until you get right down to the end. And at some point, there's some little animator who's been sitting moving pinkies a tiny amount all day, not in plasticine, but doing it in 3D Studio Max or something. So he's wiggling the thing about there. And what the program is doing is it's measuring the position of this little joint, and it's turning it into a matrix, and it's storing that in a big table that gets exported into the game. And then when you play the game, you're doing a whole bunch of matrix multiplies, the end of which is you get the little thing being drawn and it wiggles. That is really how it works. Sometimes. There are other ways of doing it, but that's a common approach. So what really matters, though, when you've got your world of objects and you're trying to make stuff happen, we discussed in the input handling lecture how you can take input events from the user and make them trigger stuff in the game. And that's what your homework is about this week. It's making sure that when you press a key, you can somehow update the position of the smiley and redraw it and have something happen. And that's pretty good, but it's not the whole story, because, of course, if you were only responsive to explicit user events, then if you took your hands off the keys, nothing would happen. The world would stop because there were no events to make anything move. What makes real-time games interesting is that they continue to function on their own, whether you're interacting with them or not, or kind of in parallel with you. And that means that there's something else going on, and the something else that's going on is time. These simulations know that time is passing, and they're reacting to that. So the whole idea of an object is it's supposed to be a fairly autonomous entity that kind of looks after its own business in the world. So it's in charge of knowing where it is and what it's doing, where it's going, and you encapsulate all that logic. Well, part of that logic is how it handles the passing of time. So one of the things that an object needs to do is to know how to update itself through time. So basically the way you do this is that all of your entities have got a method called update or something like that. And it usually takes just a single parameter, which is how much time has passed since the last time you spoke to me. So that would be the delta time parameter, it's often called. And you can do this in whatever units you like. Often it's done in milliseconds, or you might do it so that one unit means a 60th of a second, because that's the standard unit inside a game, and you would call it maybe a tick or something. But however you do it, you specify that some time has passed, and then the job of the update method for this object would be to say, okay, if that amount of time has passed, where would I be? That's all that's going on. But we do have this question of knowing how much time has passed. And the ideal way to do it is that you want to work out how much time has passed in the real world since the last time you updated this object. And you say, well, update yourself by that much to catch up with whatever's been going on in the world. But this is not universally the case. Funnily enough, not all games do it this way. What a lot of games do is they just assume that your game is going to run at 60 hertz or in the old days 30 hertz. And they just assume that the delta time parameter is always a 60th of a second or a 30th of a second, or basically whatever the standard refresh rate is of that system. This is very common in console games. Often when a console game is being designed, one of the early decisions is what frame rate are we going to shoot for. So let's say nowadays you'd say let's aim for 60. And then what happens is that, especially early on, it's quite easy to do that, because early on you haven't written very much yet. You know, your game world isn't very big. And your models are all quite low polygon because the artists haven't made the fancy ones yet. So it's all running along super fast. It's running at 60, no problem. And a lot of people write their code so that the update routine maybe doesn't even take in a time parameter. It's just called update, and it just moves things from step to step to step, basically implicitly assuming that it's a 60th of a second. But that causes this problem that I mentioned, that in a game like that, once eventually you throw enough stuff in it and it starts to get slow, the problem is maybe it's now taking more than a 60th of a second to compute the frame, and if you're really unlucky and you hit, VSync problems and you crash down to 30 frames a second, so it's now taking you a 30th of a second before you get another buffer flip, then that buffer flip took 30th of a second, but your simulation only simulated a 60th of a second passing, which is half as much, so now everything goes in slow-mo and your game starts to kind of crawl because it's got the wrong time value. So why do people do this? Why do people insist on this, using this fixed delta that causes this problem, whereas, as I've told you, the simple solution is just use a variable delta, pass in a measure of how much time has passed, and instead of just saying, new position equals old position plus velocity, you say new position equals old position plus velocity times time, you idiot. And then it would just work. So why doesn't everyone do that? Why do some people use fixed deltas?
Like easy constant?
An easy constant, that's part of it. In fact, that's most of it. Also, sometimes people seem to not really know. I've been on games where people just didn't think about this stuff very clearly, and they were maybe. The thing is, if you get to the end of the game and you are still running within your 60 FPS limit, you're fine. It doesn't come up. But in my experience, it always comes up. Towards the end, you're always getting parts where the game's too slow and this starts to go wrong. But if it's going wrong like 2 years into development and nobody really thought about it at the start, it's a hell of a problem to get yourself out of. And sometimes I think people just kind of fall into it almost by accident. What's happened is that early on the developers just assumed that they were going to keep 60 FPS because they wanted to. Maybe the designer said, I want it to be buttery smooth 60 FPS. And it's like, well, designers, I love you, but you can say all sorts of things. Doesn't bloody make it happen, does it? But these things get baked in early on and you can get in trouble. So that's sometimes the reason for it. And I've seen this happen. I've seen games that were developed hoping to be 60 FPS, and then it gets to the point where, no, we can't quite make it. We're going to have to drop to 30, and a lot of rework has to get done to compensate. All the velocities of things have to get changed. And it's a painful process and not one you want to go through. Yeah, and if you don't have the delta T thing, then you have to do a lot of ugly work to fix everything, which is a mistake. So that's pretty bad, but it can almost be defended in a couple of special cases. So you mentioned just the convenience of it being a simple constant, and that's sort of true. In fact, in the very early days, the difference between just adding the velocity versus adding velocity times time is that multiplication used to be slow. You have to go back quite a long way. We're talking about more than the 80s here, where you wouldn't want to do it that way because honestly, multiplications were an expensive operation. And the idea was that, well, don't do the multiply and it'll be faster. And as long as the delta time is very close to 1, you don't need, why waste your time multiplying by 1, you see? So if you know that you're going to be able to do this, it's okay potentially to say, I'm not going to be fancy about time. I'm going to assume that time is moving very constantly, and I'm just going to do everything I can to make sure that the game stays that way. It can also be important in network games, because in a network game, you've got what's happening on your machine, and you've got all the other players on their machines. And it turns out that if you run the same simulation, but with slightly different delta time values, you'll get different results. This is something you might kind of remember a bit from calculus, that when you're doing kind of area under the curve calculations, it depends how big your delta t is as to whether you're going to get like the right answer, and you only really get the right answer when delta t becomes infinitesimally small, right? But in real world stuff where it's always some actual value, it turns out that basically if you simulate a 30th of a second, if you simulate a 60th of a second and another 60th of a second, the end result is not the same as if you'd simulated a 30th of a second, just because the numbers end up just being slightly different. So the problem is, if you allow every computer in a network game to measure its own local clock, all of which are maybe slightly different, especially if you've got like a fast PC and a slow PC running at different frame rates. If they're running at different frame rates, they're going to produce slightly different results about where things are, and then they're going to end up disagreeing about stuff. They're going to end up disagreeing about what collided with what. And to begin with, the differences are very small, but over time they get big, and it doesn't take much for like a small difference to be the difference between, well, you either got shot or you didn't. It missed by a small amount, but now someone's either dead or not dead, and that's a big difference. So sometimes locking the frame rate or locking the time delta is used as a way of making sure that games stay in sync when they're networked. Now, you can work around that as well, but often this is the simple way of doing it. And as I say, what you're really doing in a simulation is you're doing something called numerical integration. It's kind of like, we would solve all this using calculus if we could, but it turns out you can't. So we're actually just like numerically approximating things. So we're just like doing lots of adds and multiplies, but it's never quite the truth. And the numbers do depend a little bit on the exact time deltas that you have. So that's something you have to be conscious of. So I've already said this to you, that it turns out computing 2 baby steps like that doesn't take you the same place as you'd have got to if you took one bigger step. You can probably see in your head why that's the case. At least I hope you can. Yeah. Okay. So fixed deltas have got the advantage. Also, it's easy to test with fixed deltas. If something happens and it goes wrong and you're trying to reproduce it, if the deltas are always the same, you can sort of make it happen again. Whereas if it's got variable deltas, you might actually, if it's a very subtle error, you might have a really hard time reproducing it. Like it only happens on this machine some of the time if it was going really fast, and if this other thing happened, it can be really hard to reproduce bugs that are like that. So fixed deltas have these advantages of simplicity, but they have this downside that if they go wrong in this horrible way that causes kind of slowdown effects of things. Nevertheless, I do prefer to support variable deltas where possible because of the flexibility. One of the things that's good about it, especially if you're on a PC, there's still quite a wide range of PC specs around. So you have the same game, and on one guy's machine it's maybe struggling to run at 40 frames a second, and then somebody else has got a super one that's running at 120, no problem. And you kind of want to support both extremes. You don't want to kind of force everyone to be at 60, which the slow guy can't do, and the fast guy could do faster than that if only you let him. So I quite like variability where possible. The other cute thing about variable deltas is if you can already make the time value a variable, you can play tricks with it. If it's not constant, you can scale it. And that makes it quite easy to do things like slow motion or fast forward. So when everyone, back in the day, when everyone saw The Matrix and came into work the next day and said, I've got this great idea. And the great idea was always, let's go into slow-mo during the fight scenes. And basically the way you do that is you take the delta t values and you just divide them a bit, or you multiply them by 0.8 or something, so that the amount of time that's passed inside the game world is a bit less than the amount of time that happened on the wall clock, as we call it. And that's all you do. You just change the delta t for a period, and now all the action slows down. Everything that's moving through the air moves a bit more slowly. The players all move more slowly, and presumably, as long as you're still processing the inputs, the idea is that the player has got kind of an advantage. You've got just like in the film, you've got the ability to see threats kind of with more with more lead time than you would really have, so you get more time to get out of the way. You can't actually move any faster to avoid them, but you can see what you're doing. And there was like a game called Max Payne that actually did this. It went for slow motion shootouts and things, and it was quite nice, and it was enabled because they had variable time deltas. And in fact, there are opportunities for game design here. If you have a system that lets time be variable, you can come up with a couple of cute ideas based on that, and people have done so. So if we can scale our time deltas, I just thought I would throw this in. What else can you do with them? Could you make them negative? Could you tell your game loop to start using negative scaling on time?
Yay, Prince of Persia.
And you could make the time flow in your game go backwards. At some level, you sort of could, kind of, but a lot of you are kind of looking, wait a minute, this doesn't sound quite right. And I think you know it's like, it wouldn't quite work, would it? Because there are problems. But the concept of it is nearly true. It turns out that, look, some of the laws of physics are reversible in time. There are some things that work that way. Like if you have like a swinging pendulum and you go and put time backwards, you just put negative t into the same equations. It's like, okay, it swings the other way, but it looks just the same. It's still a valid thing. If you have a ball and you throw it up and you catch it, you imagine watching the film of that backwards. It looks very similar. You can't actually tell whether you're watching that event happening through forward time or backwards time. But there are other events in the world where you can tell the difference between forward time and backward time. And this is to do with concepts like entropy, which is how you can sort of tell the difference. But one of the classic ones is like smashing a glass. Now, it's easy to smash a glass. It's a lot harder to persuade a bunch of shards to jump up off the table and all throw themselves together at exactly the right angles to join together and make a glass, which is why that is something you rarely see. But negative time is a funny idea. It does raise some questions. Could you make broken shards of glass run back together? I mean, in some sense in the game, if you absolutely recorded all the momenta of all the little fragments exactly right, you could theoretically do it. You could replay time, and all those forces that had previously caused the glass to shatter would be happening the other way around. So the collision of the fragment on the table, that force would just be applied backwards, and it would make it jump up. And at some level, you could nearly do it, but it probably wouldn't really work. And there are other things that would be strange if you reverse time. The dead would return to life, I suppose. Which leads me to this little thing. Now, so there was don't worry, I'll show it to you on YouTube because it won't embed it. So this is an old game, an old zombie game called Dead Island. Anyone heard of it? Yeah, oh, you have, right. Have you seen the trailer? Ah, okay. Well, so I'm just going to show you the Dead Island trailer. So Dead Island, not a great game apparently, but a great trailer. And the trailer tells this wonderful little story, really well made, and it's got two crossing narrative lines, one of which is going backwards in time and one's going forward. And I just think it's such a nice thing that I'm going to show it, even though some of you have already seen it. very sad. Would bring a tear to a glass eye, as my old dad used to say. That's a nice little video. But no, that's not what would happen. There are problems with making time run backwards or appear to run backwards in games. And one of the most interesting ones is that there's more than one path in the past that would lead to a particular state in the present. Basically, if you've got an object just lying still on a table somewhere, it's like, well, it could have come in there by rolling in from this side, or by rolling in from that side, or it could have fallen from the sky. And generally speaking, you don't know. There's no echo of that past has been preserved, at least not in a way you can get a hold of. So when you run in time backwards, it would just sit there. It kind of wouldn't know where it had come from, right? There's a sense in which some information got lost as the simulation was updating, and in a way that means you can't recover past states, sort of. So if you don't have a memory of the past states, you can't really figure out how to get back to them. That's sort of what I was saying, right? There are the different past paths that could exist. So this is, in the kind of more serious form of this, is related to the idea of the arrow of time, this question about how the laws of physics are somewhat time symmetrical, but not perfectly so. But it turns out you can sort of get around this in a game if you wanted to. The trick is, but you have to remember the past as it's happening, and then if you wanted time to go backwards, you would just have, you would have stored the fact that the ball came in from the right, and you would say, okay, so I'll make it, move that way now as I'm unwinding time. But you just have to cheat. You just have to remember how everything happened. And this has been done. Remember Braid, the old indie game? So Braid's got these time reversal mechanics that are a combination of lots of things, including, kind of versions of using negative t and so on. But what's really going on with Braid is just as you're playing the game, it's remembering everything that's happening. In a rather clever way. It would take a lot of memory if it was done in the obvious way, but it's remembering the state of the object, and then it's kind of compressing them, and it's just storing the deltas. It stores the difference between one thing and the next, because differences are more compressible, which is the same thing like video compression and stuff relies on the fact that one frame to the next of a video isn't a complete new copy, so it doesn't have to store the whole picture. It just stores the little bits that have changed. Same sort of idea in Braid, and that allows it to have parts of the game where you retrace your steps, and it did it by memorizing it and then kind of playing negative t. So that's just a glimpse of various things you can actually do if you make time part of your game design. And Braid is not alone in doing this. Although on the subject of Braid, so Braid was one of the first big kind of successful indie games years back, and a bunch of people, it got to the point where you could sort of make a game with a small team of people, and instead of going to like a big publisher, the way you used to have to do it and get them to put it in boxes and get boxes sent to shops, you could sell things online. It was amazing. So, if you were good enough, you got lucky, you could kind of make your own little game and get out into the world. And Braid was followed by another number of other indie games. If you know anything about Jonathan Blow, who made Braid, you'll know that these indie types they can be a bit pretentious and insufferable, if you ask me. And here's a little video about that.
Whoa, Tim! Tim from a Braid.
Yes? Do I know you?
It's me, Mario.
Oh, hey. It's a Mario.
It's a great to finally meet you. It's so nice to meet a fellow jumping platformer.
Fellow?
Yeah, your game is like mine.
Excuse me. Braid is nothing like Super Sellout 5 or whatever you're in.
Pardon?
Braid is an art house masterpiece. Nothing like your mainstream kiddie games.
Well, you rescue a princess from a castle.
It's subversive. You wouldn't understand.
But you jump on a Goombas.
Does this look like a Goomba to you?
Yes.
Okay, look. I don't just jump. I rewind time.
Like the Prince of Persia.
Yeah, but twist some puzzle pieces into the mix.
A Banjo-Kazooie.
Oh, forget it. You wouldn't understand, all right? You're just another suit.
What is, you are literally wearing a suit right now.
God, you. God. All right, hold on.
A Banjo-Kazooie.
Look, we indie games are too unique and original for you to comprehend.
Guys, my girlfriend has been captured. I better go rescue her with jumping. Yahoo!
Yeah, I wasn't gonna say anything, but I kinda have to do that too.
Yeah. So when it eventually becomes time to do your own game project, I'll maybe give you a bonus point if it's not a princess rescuing game, if you can think of a way of doing something else.
So a prince rescuing game.
Oh god damn, it's too obvious. Right, I take it back. This is the problem you get into with this stuff. But you get the idea. The medium has its cliches. So another question that comes up when you've got time, if you're not, slowing it down or speeding it up or inverting it, is actually the whole question of simultaneity, which turns out to be important, right? Because in theory, when you're doing a simulation, you've got all your objects and you're moving them. They're supposed to all move at the same time. Like in like the hypothetical real world that they're in, obviously they wouldn't just take turns. They would all just move at once, right? But it turns out that a standard computer, traditionally only had one processor and could really only do one thing at a time. So how do you make all these things move simultaneously? Now, it's true that nowadays we've got multiple cores inside our processors, but we still don't have as many cores as we have objects. So we still can't actually make things happen totally simultaneously. So this is an ongoing problem. How do you make a sequential serial computation device simulate a simultaneous parallel behavior? Well, there's a solution. We ignore it. We just forget about that problem. It's a theoretical problem, and we just don't care. It's even worse if you know that the concept of simultaneity is actually not super well defined, which is even harder to think about. So what actually happens in a game or a simulation is we update the objects one at a time. We just put them in some order, like either the order they were created in or some predetermined sorted order or something. And it's kind of always, you go through them one at a time and they all take turns. And it sort of doesn't matter because while you're moving them, again, remember double buffering and stuff? While you're moving them, you can't see anything. It's showing you the old picture. So while it's showing you the old picture, you're moving the first guy, the second guy, the third guy, the 100th guy. Once everyone's moved, then you take a picture, you do the rendering, and then you show that picture. And in a sense, well, if you move them in that order, it's not any different to if you'd moved them in any other order. They all still get where they're going, and it sort of looks the same. Doesn't it? So it doesn't really matter in what order you update things in? Is that true? Yeah, it's only partly true. Most of the time nobody notices because most of the time, yes, if you moved A and then you moved B, it's sort of the same as if you had moved B and then you had moved A. You get to the same place. Unless A and B collide with each other, or A eats B, or A and B are both chasing after the same magic object. And it's like, well, there's the magic object, you say there's B, A gets it first. No, B gets it first. Who's allowed to, who gets first shot, right? But most of the time this doesn't happen. Most of the time objects are sort of sufficiently far apart from each other and the amount of time that's passing is sufficiently small that nothing like gross happens that you can't see. Although it is true when it gets down to like fine details, there's a slight discrepancy as to who goes first, but it's small enough that it's usually not perceptible to people. And that's what we do. But it does have consequences, so it means that entity update orders have an effect on things. In particular, if you in like old games, if you had like a racing game or something like that, you've got a whole bunch of players and they're driving around trying to get across the finishing line. Well, what happens is that each one of them has got code for its update that moves to its new position and then checks to see if it's crossed the finishing line. Well, imagine if they're all going at exactly the same speed and doing exactly the same thing. They're all equally good players, they're all perfect. Who crosses the finish line first? Whoever gets updated first. Right? They're all just at the line, and whoever moves next is the one who will say, well, I crossed the line, I won. And it actually ends up just depending on your order on the list. So there's a slight player one advantage is often built in, and that player one gets updated slightly ahead of everyone else. If two players were again chasing for an object, player one has probably got a slight advantage in terms of getting it. Too small to be noticeable most of the time, but it's there in theory. Yep, that's just something I thought I would bring to your attention. Now, in theory, there are things you can do about this. I actually tried this once as an exercise. I thought it was unfair that player one always had the edge. So in every other frame, every alternate frame, I would make the game loop be updated backwards so that the advantage would flip from the guys at the front to the guys at the back. There are actually other reasons for doing this. If you think about caching, caching is where you remember things that have been recently in memory. Well, if you just update everything in your game, start to finish all the time, by the time you get to the end, all the early ones have fallen out of the cache. And when you go back to update them the next time, you get a bunch of cache misses, and they all have to be loaded in again. Whereas if you go all the way down, and then you say, now I'm going to come back, these guys are still on the cache. And they stay in there until a bit of the way back, and then you get your cache misses. So that back and forward update is sometimes called ping-ponging. And I sort of invented it, but I'm sure other people thought of it too. And you sometimes see versions of that in cache-friendly algorithms, where you realise that if you just flip-flop it, it can actually be a little bit better. But I don't think it's like a widespread thing. I think most games don't do anything like this. As I say, except for caching, things like texture caches, I think actually people figured that out and they did start to use kind of ping-pongy techniques. Even then, that's still not perfect, but it's a slight improvement. Yes, so this is on the vexed subject of complexity. I would point out that, and this is something I've lost many sleepless nights over. How does the universe do this? Right? When the universe is updating us, are we all being updated simultaneously, or are we being updated in some master order? Could you tell the difference? I don't know. But if you figure that out, that would definitely be worth a special credit in the form of a Nobel Prize for Physics, which I'm afraid I don't have the authority to hand them out. You'd need to talk to some other people, but it's just an extra exercise for those of you who think the homeworks are too easy. And I joke about it because it is kind of silly, but this has actually come up. Real people think about things like this. So remember I said at the start about, we're going to create the game from scratch, which involves creating the universe from scratch, strictly speaking. There's actually a field called digital physics, which is about this idea. It's trying to work out whether the universe is or could be a computer. The particular concern is the laws of physics as we understand them just now are essentially continuous. Like, there's an infinite number of spaces between point A and point B. There's no resolution limit to the universe according to our current ideas. It's the distance between A and B is a real number with infinite precision. You can be anywhere along this line. But we know in computers it's not like that. We know we've only got so many bits. And what some people have asked is, well, how is the universe being infinitely precise like that? Maybe it turns out it's actually got a resolution that's really, really high. That there's some tiny quantization of space, and that things are either at that bit of space or on the next block along, and that space and time might be quantized. Wild speculative stuff, but not entire. But there are people who are not entirely crazy who think about this, and one of them is Konrad Zuse, who's one of the first people to actually build a real computer, the one I mentioned way back. He was doing it in the 30s in Germany. He wrote a thing called Calculating Space, which is his elaborate theory or speculation that possibly the laws of physics might have a digital character to them. They might be quantizable. This is something I've looked into a bit, although I've never had time to read it properly. It's a fascinating idea, though. Now, as I understand it, what Konrad was speculating about was that the laws of physics might turn out to be like what you would call a cellular automata, and that it might turn out there really were discrete elements in physics, which is kind of partly what quantum physics is kind of in some ways is moving in that as a sort of step in that kind of direction. I don't think he was going all out and saying that the universe is a computer simulation, although the two ideas got very entwined. because if you think the universe is a simulation, you need to think the universe is computable, in the sense of computable by Turing machines or some other equivalent thing. So that's actually an idea that's been kicking around for a long time. Look, are the laws of physics computable, which would mean, can you write computer programs that would simulate physics to arbitrary correctness? And if you want to be crazy and you think about that, you could ask, are we living in one? I don't think we are, right? But it's an idea that people kick about. Elon Musk apparently thinks that we are, but he's a bit of an idiot at times. So here's one more thing about a time manipulation mechanic. This one is really interesting because, well, for a number of reasons. One is it's very related to your homework this week, because your homework this week, if you think about it, as I said at the start, you can move things around now with the keys and the mouse and stuff, right? But they only move when you move, right? You move the keys and the thing moves, and they don't have inertia. It's like when you press W, it moves, but if you let it go, it isn't going to keep moving. And please do it like that, right? This exercise is about it being input-driven. Don't try and be clever and make the thing move on its own. Don't add a time element, because although I'm telling you about it now, I haven't shown you how to actually do it. So your current homework has got this property that in a sense, time only passes in that world when you're pressing the keys. And somebody came up with a game that's based on the same premise, where time in this game only flows when the player moves. If you stand still, the game stands still as well. And when you move, it moves. And basically, it's doing a kind of jokey version of the exact same thing I'm asking you to do, that in this world, it's only updated when the player's inputs occur. And that game is called Superhot.
Isn't looking around exclusive though, so that doesn't move for a time.
It actually, when you move around, time moves very slowly in Superhot. They've actually slightly finessed it, but the basic idea is that the pitch is that the time only moves when you move. The reality is there's actually a little bit of background time moving for their own subtle reasons. The Superhot's really interesting, and actually when I first spotted it many years ago, it was a web game, but it was written in Flash, this old web player thing that you can't get anymore because Steve Jobs said he didn't like it, so everyone just decided to abandon it. Actually, he was right on that occasion. It was a bad idea, but he couldn't make it work on iPads, so he basically just bullied the industry into getting rid of it. It's for the best. So the thing is, the old Superhot on the web doesn't exist anymore. You can't get it, but they've still got their old website. And there was a time when they had to get rid of the Flash version, but you could download a version for your PC and play it. How many of you played Superhot? It's actually pretty good, right? I told you all that without checking how many. It's like, I'll check whether you've heard the Charles Babbage and I'll talk about it for 20 minutes, and I won't check whether you've played a game that you probably have played. The Superhot's great, and the nice thing about Superhot is that after that its period on the web and after it became a little PC game, it went sort of full on and became a VR game. How many of you have played it in VR? Only a couple, but yes, me too. I love it in VR, and it's great. I'm like a VR booster. I enjoy VR games. So this is this just, yeah. So this is the VR version of.
It's also really cool that they would, after you finish a level, they would play it in real time.
Does it do that?
Yeah, when you finish,
Yeah. Oh, I see.
Yeah.
I mean, I definitely have played multiple versions of this over time, and I've forgotten that particular aspect, but they do lots of cool things. But I nowadays play it on VR, and that was the trailer for the old the Steam or the PC version. I've got a thing here. It's not the trailer for the VR one, although I did find that at some point. Should we try that? Don't know if I really need to. Let's see what it looks like. Yeah. That is quite nice. Yeah, I love playing that. I'm going to play that when I go home again. Sit around in my living room, waving my arms around like an idiot, pretending that I'm Neo. Yep, that's what I'm going to be doing. But the funniest thing about this is this review of the VR one, which I just thought was hilarious. I have to share it with you. So this guy, if I remember correctly, he sounds like he's of an Irish persuasion, and you know what the Irish are like.
Top of the morning, you laddies. My name is Jacksepticeye, and
Irish.
welcome to Super Hard VR Edition. I've been waiting for ages for this. Yes, I know what you're telling me to do, to pick up my controllers, but I'm not going to do it because I don't want to click on this gun. Ever since Super Hot was announced, and VR was kind of announced around the same time, I've been waiting for this for ages.
Yeah.
And
Okay, let's get to the bit where he plays.
You hit the chair. Yeah! Super hot! Wow! Oh, fucking awesome. Okay, what else you got for me? Are you ready to play? What else have I been doing all this time? Show your dedication. Oh, okay. Oh! Oh my god! Holy shit! I had to show my dedication by killing myself. Well, killing yourself in the game. Because after all, whoa! That's what they keep telling you in all these VR games, is that killing yourself in the game is the only way to escape the game. And that's what always happens in all VR media. Oh, yeah. I got my little sensors in here as well. So, it's super meta now, because before when we played it, we were a guy sitting in his room and we had to walk up behind him and shoot him. But now that we're actually in VR and we have a VR headset in real life, playing a VR game, like, it's so bizarre. Also, I know I've said that these Oculus Rift controllers are pretty good, but can we please get these? The gloves that actually match all our fingers? That would be really cool. Okay, let's head back in. Woo! Let's put on the headset. Or are you just going to lower it onto my head? Please put on your headset. Oh, okay. Oh, that's awesome! That's so bizarre as well! Now that I'm actually in VR, heading into a game, heading into VR, heading into a game. That's so awesome! Boosh! Oh, did you all see that? There's a helicopter over there. Oh god. Oh shit. Ah! Oh! The dude from before! Uh-oh. Did you shoot me? Fuck! This dude! Oh, I have to start the whole thing over again? This dude fell out. I was down there! He's still falling! That's fucking cool! Did I get everyone? Yeah, hell yeah, I did. That was so awesome. Okay, I'm saying the fucking same things over and over again. I can't say how awesome this actually is. Like, having played the game normally and now seeing it in VR, it's fucking awesome. Oh god. Give me your fucking gun. You only have fists. Yes! Oh yeah! Hello? Calculator? Can you call my wife and tell her that I'm sexy as hell? There's a fucking gun down here all this time. Why didn't you tell me, you fuck? Good. Yes, guns are good. Oh god, I thought he fell over.
And it goes on like that. It was very enjoyable. I'll leave that one with you if you like. And that, in fact, is what I wanted to talk about today. So, get an idea of how simulations might work. Update function, delta time, fixed or constant, depending on how competent you are. And the fact that you can muck about with time potentially as a game element. That was mainly what I was trying to get across today. Job done.